Welcome to this explainer. Today, we're diving into some physical marvels that honestly sound straight out of a sci-fi movie, but are totally grounded in modern material science. We're talking about polymers that can literally remember their original shapes, perfectly heal their own structural wounds, and completely change forms on demand. It is fascinating stuff, so let's jump right in. Here is our quick roadmap for today. We'll start off by looking at materials with a memory, break down how shape memory works, explore the specific heat and chemical triggers, discuss a massive leap forward called the Vitrimer breakthrough, and then wrap things up with some mind-blowing applications in future tech and space manufacturing. All right, starting with section 1, materials with a memory. I want you to picture this. Imagine a crushed, heavily mangled object. Maybe it's a piece of plastic packaging or even a highly engineered structural support. Now, what if that object could spontaneously snap perfectly back into its pristine, original form without taking any permanent damage whatsoever? It sounds a bit like magic, right? But it's actually a very real mechanical property that engineers are actively harnessing today. We call this the shape memory effect, or SME. Now, what's really interesting here is the concept of a high-energy barrier. See, unlike a normal rubber band that instantly snaps back the second you let go of it, these SME materials actually freeze their deformed state. They hold on to that stored elastic energy indefinitely, kind of like a paused video, until a very specific trigger releases it, allowing them to finally cross that energy barrier and dramatically return to their original form. You can actually see the macro impact of this effect right here, with this biocompatible PLA spring slowly recovering its original spiral shape. Just think about the biomedical applications for a second. You could have a tiny PLA stent that gets compressed all the way down to fit inside a surgical catheter. It gets inserted into a patient's body, and then it expands to its original shape to keep an artery open. And the best part? If it ever needs to be removed, a simple stimulus can shrink it right back down for safe extraction. It's brilliant. Moving on to section 2, how shape memory works. Let's peek behind the curtain at the mechanics. So how do they actually pull this off? Well, it builds into a repeatable process known as the programming cycle, which fundamentally relies on storing elastic energy and locking it securely in place. First, you heat the material to soften it. Second, you apply physical force to deform it into a temporary shape. Third, you cool it down to freeze that new shape in place. And finally, whenever you're ready, you apply a trigger to recover the original shape. To simplify these highly complex chemical networks, I want you to think of the mechanics as tightly coiled elastic springs temporarily trapped inside a switchable matrix of ice. The elastic part stores the driving energy, while the transition part acts like the ice, freezing everything in its temporary shape. This happens through a few different mechanisms, like shifting between a glassy and rubbery state, or using a dual-component system where an elastic matrix surrounds meltable inclusions. It's almost like having a rigid wax trapped inside a flexible silicone. Okay, let's move to section 3, heat and chemical triggers. Here's the really cool part. We don't always need an oven or a heat gun to activate this recovery. While thermally induced SME does use external heat to cross that energy barrier, chemically induced SME takes a completely different, almost sneaky route. Simply exposing a programmed polymer to a chemical, like water or ethanol, can actually drop its transition temperature from the inside out. This triggers an automatic recovery right there at room temperature. If you look closely at this boundary line, you can clearly see a chemical solvent physically diffusing into the polymer structure. As that ethanol penetrates the PMMA polymer, it softens the transition component as it moves deeper inward. You get this incredibly distinct line between the softened, ethanol-infused polymer and the rigid, completely untouched polymer ahead of it. It perfectly illustrates exactly how chemical triggers work at a microscopic level. This brings us to section 4, the Vitrimer breakthrough. Now, for decades, engineers were kind of stuck between a rock and a hard place. You either chose thermosets, which give you permanent cross-linked networks with phenomenal stability, but are completely impossible to melt and recycle, or you went with thermoplastics, which are super easy to melt and reshape, but lose all their structural strength at high temperatures. Enter Vitrimers. These things are an absolute game changer. They're the ultimate best of both worlds hybrid, because they feature what are called dissociative covalent adaptable networks. Now, in plain English, that simply means we can temporarily erase and redraw their cross-linked network on demand just by applying targeted heat. So they behave like ultra-strong thermosets at room temperature, but they can actually flow like thermoplastics when heated. To visualize just how wild this is, check out this coin impression.
What we have here is a polymer that has a permanent shape of a coin impressed right into it. But because it's a vitromer, we can superimpose a new, temporary shape directly on top of that permanent shape without destroying the underlying material. And get this, if we apply heat again, the temporary impression just wipes away, leaving the permanent one perfectly intact underneath.
All right, let's look at the big picture in Section 5, Future Tech and Space Manufacturing. So, why does all this microscopic chemistry actually matter to us? Well, for starters, a severely scratched or cut surface doesn't mean a ruined product anymore. Thanks to that reversible network we just talked about, applying a very precise temperature window allows a vitromer to literally heal its own structural cuts. The material flows just enough to repair the microscopic damage and bridge the gap of a deep slice, all while completely maintaining its original surface pattern. It is also a massive deal for wearable tech. By combining vitromers with elastic textiles like spandex, we can create instant-fit garments and medical splints. They can be molded exactly to a patient's anatomy just using body temperature. But unlike traditional rigid splints, they remain totally flexible and elastic, giving you vital support without sacrificing an ounce of comfort or mobility. And the applications don't stop at Earth's atmosphere. Think about trying to deploy a massive solar panel on a satellite in zero gravity. Standard hinges tend to snap open violently, which creates turbulence that can easily damage delicate instruments. But vitromers actually have a unique shear thickening effect when they get hot. So, by using a vitromer-coated hinge, the material inherently thickens under the stress of deployment, safely absorbing the impact and smoothly unfolding the panel. Speaking of space, vitromers are completely flipping the script on 3D printing. Because they can be cross-linked while remaining totally solid and transparent, they unlock the ability to 3D print reliable, complex parts directly in highly turbulent environments, like out at sea or on orbital space missions. You don't have to worry about liquid resins floating away in zero gravity or sloshing around during extreme vibrations anymore. Which leaves us with this final thought to chew on. If the very materials we use to build our world can heal their own wounds, remember their past shapes, adapt to our bodies on the fly, and even be 3D printed in the extreme void of space, how will this reshape the entire future of engineering? The boundary between a rigid, static object and a programmable machine is fading really fast. Thanks so much for joining me on this explainer, and keep questioning the materials around you.